this computer and then share the screen. I hope it's this one, and share. Hope you can quickly check. You see this one. Okay, that's not the one I should. Okay. I thought it. Oh yeah, this one. It's okay, and now I think we need to put this down. Great. Okay, Roger.
Yes?
Yes, the floor.
Am I visible then?
Yes, you are.
Okay, all right, because,
Yeah. It's
Okay.
Good. All is good.
all right, thanks very much, Tina. Thank you all for coming, especially Johannes Bracher. Thanks for coming. Very good to see you. We'll schedule your talk for next fall. Okay, convolution of scale invariant continuous ranked probability scores. First question is, who cares, right? So, it doesn't, oh, it does advance. See, I can't see what's on the screen there. Can you? Can you move it somewhere? Can you put it down at the bottom?
You also see
hell.
no, this is not for the others.
Yeah, but so I can't see anyway. I probably know what it says. So CRISP, continuous rank probability scores, is a continuous version of the Breyer score. That's one thing that makes it interesting because Breyer score is very popular. It's also been used in COVID modeling, and there's some references here about that. And Ernani, who is in the public here, was participating in another study using the classical model to analyze probabilistic forecasts of the COVID models. And Ernani asked me to explain what this was. So, and Johannes Bracher is, you see, is an author of this thing, the applied COVID models. He's in the public today, so thank you for coming. And okay, let's go. Scoring rules were introduced by De Finetti in 1937 as a tool for eliciting subjective probabilities. And the idea in one line is this: suppose you believe a distribution S and you are asked to report a distribution, and you report P, and you're going to be scored on the basis of P and some observations. And if that scoring rule is strictly proper, then you will get your best expected score if and only if P equals S. So if and only if you say what you really believe. That was the idea of the scoring rules originally. And as I said, they were designed to reward honesty in elicitation. And one may remark that rewarding honesty is not the same as rewarding quality per definition. And here's a very simple example to show why. Consider a simple coin tossing experiment. And so suppose you report that the probability of heads is 1/2. Now, on all of the familiar scoring rules, you get the same score with a head as with a tail, because the probability of heads is 1/2 and probability of tails is also 1/2. So your score doesn't depend on the outcome. And if you assess 100 times with this thing, it means that your score, if you add up your scores over 100 coin tosses, your sum score is independent of the outcome sequence. So you get the same score whether you have 50% heads and 50% tails or 100% tails. And so this shows a very simple theorem that the same scores does not mean the same quality. Okay, so now we talk about CPRS and the Breyer score. And the first example just concerns the Breyer score. And we are considering 1,000 next day forecasts of rain. And on 500 of the next days, it rains. And we're going to look at 3 experts. So Professor Green here, he assigns 100 days to each of these 10 probability bins. So for 100 days, he says the probability is 5%, for 100, 15%, and so on. And then we look here at the realizations. On 5 of those 5% days, it actually rains. On 15 of the 15% days, it rains, and so on and so forth. So the, what is this, orange expert, he also assigns 100 days to each probability bin, but the outcomes are as follows. For the first 5 bins, it never rains. None of these 100 days in each of these 5 bins sees any rain on the next day. And for the rest of the 5 bins, it rains every day. And expert number 3 also assigns 100 days to each bin, and he's just a mixture of the first 2 experts, really. So he gets 25 rainy days in the 5% bin. He gets 75 rainy days in the 15% bin, 0 rainy days from 25 to 55% bins, and then for the rest, he gets all rain. So how does the Breyer score reward these assessments? Well, here it is. The Breyer score, by the way, is 2 times 1 minus the quadratic score. So it is negatively sensed on the 0-1 interval. 0 is the best, 1 is the worst. So let's just look at the scores. They're here over on the right. Professor Green gets a score of 0.1675. Professor Orange gets a score of 0.0825. That's half. That's much better than Professor Green. And Professor Gray down here, he gets a score also 0.1675, the same as the first guy. So why does this happen? Let's analyze this a little bit. The Breyer score can be broken down into an additive decomposition of a calibration component and a resolution component. So calibration rewards if your empirical distribution is close to the predicted distribution. So here you see for the green expert, his empirical distribution is always exactly equal to his forecast probability, and therefore the contribution from the calibration term is 0 for all 10 bins. The resolution score, this rewards the difference between the sampling distribution in a given bin and the overall distribution here. So the overall distribution is 500 out of 1,000. So the more this distribution differs from 1/2, the higher it is able to resolve the sample. So resolution rewards resolving the sample. So you see here, 5 out of 100 is not too close to 1 out of 2. So there's a very low contribution from this bin, but as you go up towards the middle, the contribution gets bigger, and then it tapers off again as you get to the 95% bin. So you add these numbers up, 0 for the calibration component, 1.675 for the resolution component. Now you look at the Professor Orange down here, you see here, for every bin, his sampling distribution is maximally different from the overall distribution, right? The overall distribution is 50/50. Here it's 0, 1, 0, 1, 0, 1. Here it's 1, 1, 1 out of 1, 1 out of 1, so on. So he gets a 0 component for the resolution term, and his calibration is scored up here. So he's not doing so badly for the 5% bin, but as you get up to the 45% and 55% bin, he's getting a contribution to his score from the calibration score. But note that that's less than the contribution of the resolution to the green X. So when you add all these things up, he comes out with a much better score, although his sample frequencies are very different from what he predicts. The point is that they better resolve the sampling distribution. And the gray expert, he's just a mixture of these two things and is chosen such that mirabile dictu, it comes out to exactly the same number as Professor Green. So here again, the same story, same scores do not imply the same quality. And you see, in fact, that expert 2 gets a better score being wrong than expert 1. So you might be happy with that, you might not be happy with that, but in any case, it might be something you want to know if you're going to use the Breyer score. Okay. That went at warp speed. I'm going to slow down a little bit now. For the continuous ranked probability scores, the expert gives a cumulative distribution function f of x, f sub x, and that's his distribution function that he attributes to a random variable y. And we're going to observe y, and based on the observation of little y, we want to give this expert a score. And the Cripps score is given by this thing. So here you see if X is bigger than Y, then this term is 1. This is the indicator function for this event. And so you get 1 minus f of X squared, which is the complementary distribution function. And if X is less than Y, then this term is 0. So you just get the cumulative distribution function squared. Now you can do a little bit of calculus on this. So this integral can be split from 0 to Y, and then from Y to infinity. You take the derivative with respect to Y, set it equal to 0, and you will see that the value of Y, which gives him the least score, the smallest score, that is the best score, that happens if Y is equal to the median of X. It's sort of obvious once you think about it. And so, well, that's something you want to know. And then we're ultimately interested in the expectation of this score, where Y is now a random variable. Well, that's kind of hard to compute because we don't have the distribution of this guy. So this is the beginning of a long discussion, which I don't want to have here because we're going down a different road. But just to point out that whatever this distribution of X is, he's going to get his maximal score, or I'm sorry, his best score, which is his minimal score, for the distribution of Y, where Y is concentrated on the median of all of these guys, which in general is going to be very different from the distribution of X. So again, he gets a better score by being wrong than by being right. But what we really want to do is test the hypothesis that the experts' forecasted distribution, F sub X, is equal to the distribution of Y. We want to test that hypothesis. Okay. So, but to get a little more numerical insight, we're just going to go through a few little computations. Assume that Y is uniformly distributed here on the 0, 1 interval. So it has this as its cumulative distribution function. And now we've got Professor Green here. And Professor Green thinks it's uniformly distributed on the interval 0, 1/2. I'm sorry, 0.7. And Professor Red thinks it's uniformly distributed on the interval 0.3 to 0.7. Now, if you do the math, which I'm not going to do, you will see that these two scores are exactly the same. So what's happening here is that Professor Red is getting a larger statistical error, but he's giving a more informative or more sharp distribution. And the decrease of his statistical performance is compensated by his increase in sharpness. So maybe that's what you want, maybe it isn't what you want, but you want to know that that's the way it is. But this is a general result. It holds for any H, which is bigger than 1/2. So the uniform distribution on LH will get the same score as the distribution on 0H for any H bigger than 1/2, in particular for H equal to 1/2. So here we now have Professor Green says it's uniform on the interval 0, 1/2. And Professor Red says it's concentrated at the value 1/2. And these guys get the same score. And of course, this is all a very simple example, but if you think about having a sequence of distributions which converge to this distribution function or this one, then their scores are also going to converge. So it's not really about having such small support for these distributions.
Quickly, Roger, this is
Sure.
based on a very strong assumption of normality, right?
No, there's no assumption of normality.
No, I'm talking about the underlying density. If the underlying density is not normal, then some of this will fall apart.
No, the density of Y is uniform on the 0, 1 interval.
And that's an assumption. That's my point.
That's an example. Yeah,
Okay.
it's an example. So in order to get an example, you have to fill in some things here, right?
Yeah, because my argument is if the underlying density were log normal, for example, or beta distribution, for example, then it's likely that the equality we have here will not hold.
Oh, sure. No, it absolutely won't hold. No,
Okay.
it absolutely won't hold.
Okay, thank you.
It depends on the distribution. But the point of the example is to show that this score, like any of these scores, they involve a trade-off between statistical accuracy and let's call it informativeness. So
Okay.
you can lose statistical accuracy and compensate for it by being more informative.
I see.
And this is a very simple example that you can compute relatively easily. If you put a beta distribution on here, I don't think, yeah, I don't think, that won't be a happy day, I think. Okay?
Yes, thank you very much.
Okay. Please interrupt anybody, please interrupt. So what we want to do is make a statistical test based on this continuous rank probability score. And what we're going to do is apply the probability integral transform. So we take this variable x and we're going to hit it with its own cumulative distribution function. So that means if x realizes, say, the 35th percentile of its distribution, then this number here is 0.35. So this just converts x to a uniform variable. And it's scale independent. It's just a uniform variable on 0, 1. If you change from meters to millimeters and you adapt the cumulative distribution appropriately, you'll still get the same distribution on 0, 1. Now for y, we're going to take y and hit it with the cumulative distribution function of x. So this guy, which we call v, is concentrated on the 0, 1 interval, but it's not necessarily uniform. That's what we want to test. Okay, so let's do a little math here. This CRIPS evaluated at the uniform distribution function for some number v between 0 and 1 is blah, 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 is equal to blah, 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 is equal to blah, blah, blah. And you see that this score is going to be concentrated on the interval between 1/12 and 1/3. And if you do a little bit of more math, this thing here, the distribution of this CRIPS, when I let v become a random variable, is going to be the distribution of this thing, where v is some unknown distribution on the 0, 1 interval. And if you work this out, the cubic terms drop out and you get this quadratic here, 1/3 minus v plus v squared. We don't know what v is, but whatever it is, that's going to be the distribution. Okay, but now let's assume that v is uniform on 0, 1. Okay, so what do we know then? Well, if v is equal to 1/2, that's the median, it's going to have its minimal value, which is 1/12. And if z is equal to 1 or 0, it's going to have its maximum value, which is 1/3. And for any two numbers which are symmetric about a half, say 0.4 and 0.6, you're going to get exactly the same score, right? So if I have one expert who gets a score of 0.2 on the first variable and 0.8 on the second variable, he's going to get the same score as another expert who gets 0.2 on both variables, right? We're going to come back to that. So this is a cumulative distribution function, and this is the density. So we can compute the cumulative distribution function. It's a nice exercise for students. So what is the probability that this CRISP evaluated at v is going to be less than x? Well, that's the root of 4x minus 1/3. If that's not obvious, then you just look at it this way. Look, suppose x is equal to 0.2. So I take 0.2, I project these points down here, which means I'm taking the root of this quadratic when I subtract 0.2, and I get these two numbers. And so the mass between these two numbers is this probability up here. And if v is assumed to be uniform, then it's just going to be the length of this interval. So that's all easy peasy. Now, we get another nice idea. Instead of just looking at CRPS, let's give it a linear transform, 4 times CRPS minus 1/3. So, well, okay, it's trivial math, but I'm not going to do it. If you compute the cumulative distribution function of z at the point x, you will find root x. Ah, bingo. We know where we are. So if I recall the uniform distribution squared, the probability that that squared uniform is less than x That's nothing else than the probability that u is less than the positive root of x, which is the positive root of x. That means that this z guy up here, he's distributed as the square of a uniform variable. Yeah, cute, huh? Yeah, okay. So now we don't want to add the scores for a bunch of observations. We want to take the distribution of their sum. So that is the distribution of this guy Sn, which is the sum of independent squared uniforms. What is that distribution? Well, it should be intuitively obvious that that probability is 1/6 plus s over n plus 1 over pi times the imaginary part of the infinite sum of these Fresnel integrals. And if that's not clear to you, you can ask Tina. And she will explain it, right? Any questions? So, yeah, we experience this as being extremely cool, that you can get the closed form of this convolution for any n, and it actually works. And Tina implemented this in R, and we've got applause. Yes, absolutely. Yeah. So, well, this was in the literature, right? But it's you got to dig to get it out, right? So, if we look at the density of the twofold convolution, let me just go back here. This is the density of one of these guys, strongly concentrated at 0. And so now we go to the convolution of two of them, and look at this density. It's uniform on the 0-1 interval, and then it's going down here to 2. So if I showed you this density and I say, where does this density come from? How many would guess that it's the sum of two independent squared uniforms, right? This is a miracle. And if you look at the density of a threefold convolution, you get this guy, right? Weird. It's going to normal, right? But it's not gonna get there anytime soon, right? Yeah. So we've got the exact distribution for this. So, okay. Oops, what the hell is this? Oh, I got it. Okay. Okay. So Tina implemented this in R, and here in the red is the theoretical distribution. You see for a twofold convolution, it's a straight line up to 1, and then it starts. And then for the threefold contribution, you get this. So it really does work. So now we want to use this to make a statistical test based on CRIPS. So how does that work? We've got a whole bunch of variables xi, and for each xi, the expert gives us his cumulative distribution function, f of xi, applied to the realization, which is yi. And we call that thing, we multiply it by 4, subtract 1/3, and we call that zi. And so now, if we have n calibration variables for which we know the true values, the statistical accuracy score is going to be 1 minus the probability that Si is less than the sum of all these Z's, right? So how to interpret that? So we know that if f of y is equal to the median, then this score is going to be 0, right? So the minimum value of CRISP is 1/12. So 1/12 times 4 is 1/3. 1/3 minus 1/3 is 0. So you're going to get the score 0 if y is actually the median of all of the xi's. And so this thing is going to be 0. And the probability that Sn is less than or equal to 0 is 0. So this guy is going to be 1. On the other hand, which is more frequent, the yi's are far away from the median. They're in the tails of the distribution. And then this guy is going to be large. So the probability that the sum is going to be less than this thing is going to be almost 1. And so the statistical accuracy score will be close to 0. Okay. This is the same sort of thing that we do in the classical model, but we're now doing it with the CRISP. So let's look at some data. I'm going to be using the data that was published in the 2021 in the International Journal of Forecasting. Our data has grown a lot since then, but this is the last data set that was published. So we have 526 experts, and for each of them, they're in various panels, and they assess different quantities and different numbers of calibration variables. But if I just score them all with this CRISP, I'm going to be getting a statistical accuracy score. And if I order the CRISP scores from low to high, I get them on this red line here. Now, for each point on this red line, there is one and only one blue point that corresponds to it. And that is the statistical accuracy scores that we get with the classical model, which is the standard, chi-square, 2 times the log likelihood ratio, asymptotic approximation as chi-square. So there's the same drift here to these numbers, but there's a hell of a lot of scatter. So we're interested in what's causing this scatter. So, as I said, this CRISP score is not sensitive to a location bias. So if I take all the scores and all the ones that are above 0.5, I just reflect them around 0.5 and put them on the other side, then the median is way off, but he gets exactly the same CRISP scores. So that's what we mean by location bias, and we can quantify that as looking at the absolute value of the percentage of realizations that's above the median minus 50%. So if all of the observations are above the median, then this thing is equal to 0.5. If half of the realizations are above and half are below, then this thing is equal to 0. So here, with this definition of location bias, here are the location biases for all of the experts. So you see here, for 11 experts, I think it's 11, the location bias is 0.5, which means all of the realizations were either above or all were below. And it goes on down here. There was actually about 70 experts who had exactly half of the realizations above the median and half below. And then it goes on up. So if we just pick a number, say 0.2, we're going to look at that. So these are guys whose percentage of realizations above the median was either above 0.7 or below 0.3. Okay, so now I take that same picture and I put a black circle around all of those experts whose location bias was at least 0.2. And you see that's pretty many. And you see they are overwhelmingly below the red line, which means that the classical model is penalizing their location bias, but CRISP is not. So this goes some way to explain what this scatter, where it's producing this scatter. Now, these red things, these are the guys, I think there's 11 of them, whose location bias is 50%. So these are the people who have either all realizations above the median or all below. And you see, these tend to be at the low end here. So this again emphasizes that CRISP is not seeing the location bias. Okay? That might be part of the explanation. If I just look at those experts who had no location bias, there are 70 of them, and we compare them with the CRISP scores. Well, the scatter is smaller, apparently, to the eye. That's just eyeballing, but just to give the idea, it looks as if the location bias is explaining a good deal of the scatter. Now, we can also consider the underconfidence bias. So I hadn't shown you this. This is new when I was preparing the talk. So I thought, why don't we just look at underconfidence? Normally, we think that underconfidence is very rare among experts, but it's not actually that rare. So there are actually 74 of these experts who have less than 90% of the realizations wrong. Stop. Now, I'm going the wrong way. There are 74 experts for whom the percentage of realizations between their 5 and 95% value is more than 90%. They capture more than they're supposed to within their confidence band. We would have thought, you learn by looking at data. Well, we thought, well, that almost never happens, but in fact, it does happen because many of these studies involve a fairly large number of calibration variables. So it does turn up. And you see here also, they tend to be on the low side of this line, except when you get up here in the very top. So the underconfidence bias may also be contributing to this. The last thing to note is what's called the MAPE. So the MAPE is the, well, I can't read it on my screen, but mean absolute percentage error. And there's a formula up there that tells us what it is. There's a lot of ways of measuring the error in a point forecast. all of them have advantages and disadvantages. Usually they have more disadvantages than advantages, but this one is the most popular. And its only real problem is if your realization is close to zero, then it becomes very unstable. So I'm going to look at the MAPE scores of all of the experts, but I'm going to stop at 2. I mean, the highest MAPE score in this data set was over 1 million, right? And if I put that guy in, then all of the other things will just be in a little cloud here around 0. So let's stop at 2. That's plenty of MAPE, right? And so if I score, there's 326 experts who survived that truncation. And this blue line represents their MAPE scores ordered from low to high. And the MAPE scores you read off on this right axis, okay? Now, for each point here, let me give you a point here. Let's pick this guy. This is a black point, so that means this is showing you the statistical accuracy according to CRISP. And that is 0.8. And if I travel down towards this blue line, you see there's going to be one and exactly one orange point. And there it is, right on that line. That's the same expert. And this thing is giving his statistical accuracy score according to the classical model. And that's 0.2. So this is showing you that for the very low values of MAPE, they tend to have a higher statistical accuracy score under CRISP than under the CM. So this means if we weigh our experts according to statistical accuracy with CRISP, we're going to expect to get better MAPE scores than with the classical model. So let's conclude. Statistic, sorry. No, you want MAPE to be small. You want MAPE to be small. Yeah, it's the distance to the truth in a scale invariant form. So you got to divide by something of the scale, of the same scale, in order to get something that's scale invariant. So you divide by, you could divide by other things, but you divide by the realization and you get the MAPE. So low scores are good, and you can expect that CRPS as a weighting system will tend to get better MAPE scores. And the trend lines are here. You see these black lines is for CRISP, and this is, there may not be a big effect, but it certainly is an effect, and it's probably worth going for. So conclusions, the statistical accuracy test with CRISP has the exact distribution of the sum. This is quite a big deal, right? Applause, Tina. And this gets 2 smileys, right? And the statistical accuracy test with CRISP is more sensitive to low MAPE values. That's 1 smile. That's nice, but I don't think the effect is as big as you might like, but it's nice. On the other hand, statistical accuracy with CRISP is insensitive to location, to underconfidence bias. That's a frown. And it's insensitive to the location bias. That's a little more painful. That's 2 frowns. But now I look to the mathematicians in the audience and say, look, guys, can't we fix this thing? Can't we tweak this score somehow to make it sensitive to location bias? I bet we can. Okay, so I didn't see Guus Rongen in the public. Are you there, Guus? He's not. He's in New Zealand, so it would be about 2 in the morning. So I won't show his slide because I can't explain it. So that's the end of the talk.
Yes.
Thanks for listening.
Thanks. Stop this and then stop recording.